In this video, we are going to look at a method to prove that a language is not context-free. So remember that when we study regular languages, we have a pumping lemma for regular languages. So in other words, if a language is regular, then for any string that's long enough, then there will be a portion of it that you can loop. So in other words, you have so let's say you have a regular language, then you have a DFA, then you're gonna have a DFA, right? So you're gonna have a DFA, and then for any string that's long enough, and then of course say it is longer than the number of states, then that means there will be at least 2 states here that are the same on this accepting pass. So then of course this itself, because they are the same, so this part is a looping. So the whole string is X, and we can say this is a Y, so you can remove this Y, the string is still accepted. You can loop this Y many times, you can still get a string that's accepted. So that is the pumping lemma for regular languages. So similarly, for context-free languages, we have a pumping lemma as well, but in this case, instead of looking at a single pass for the DFA, we're going to look at a derivation tree. Okay, so, and then as long as the tree is high enough, then there will be let's say this derivation tree means we start from a context-free grammar. So that means there will be at least one variable on a pass that appears more than once. So then, of course, from that point, you still have a pumping lemma. Okay, so that's what's going to be. So let's first look at this slide. Okay, so we want to know whether this language A to the n followed by B to the n followed by C to the n for any integer n is accepted by a PDA. So in other words, we want to know whether this language is context-free. Okay, so we know that A to the n followed by B to the n for any n is context-free. But once you add one more term here, then a PDA, now remember, PDA can memorize some patterns, but once you have A to the n, B to the n, and C to the n, if you do matching, okay, so you can pair off A to the n and B to the n, but then what happened to the C to the n? So how do you do this matching? So then you suspect that a stack memory is not going to work. However, of course, you still need to find a mathematical proof that it really, this language is really not a context-free language. But on the other hand, if you have this language, say A to the n followed by B to the n plus m, and then followed by C to the m, then of course you can use a stack memory to recognize this string, right? So you first push A to the n's into the stack, you pop B to the n many b's off, you pop n many b's off, and then you push again, right? Once you pop off everything, when your stack is empty, you push B again, you have m copies of B, to be in the stack, then you can do a matching with C's, right? So this is a context free, for instance. So you can use a PDA, you can also use a CFG in here. So here is you generate A. So S goes to AB, then A generates the same number of A's followed by, generates number of A's then followed by the same number of B's, and then B generates number of B's followed by the same number of C's. Okay, so that is context free. But this, we suspect that this language is not. So how do we prove it? So as we said earlier, we can still have a pumping lemma. For FA, we use a pass. And for context-free language, we know that it's generated by a context-free grammar. So you start from S, right? Then you apply, so you apply certain rules, and then at the bottom, you get your string X. So then when this height is, so this is height of the tree for this X. So if this height is longer than, let's say a number of, say this is high enough. So this height is greater than the number of variables. That means then there will be a variable t somewhere that appears more than once. Okay, so so then we can do a pumping lemma. Right, so now let's move on to the next. Let's first see a picture first. Okay, so as long as your height is, so now we just, so let's say we start from a variable t. Okay, and if this height is big enough, then there will be at least one variable that appears more than once. Okay, because you only have these many variables on a pass. So let's say this R appears here, this R appears here, and then we can look at. So we can break your input into 5 segments, right? So for the lowest R, you're going here. We call it X. So this part is X. And between these two R's, we'll call that V on the left, and this is Y on the right of this X. And then from R to T, so that portion is U, that portion is Z. So here you can see we can remove V, you can remove Y, you can still derive that sentence, derive that string because you have R here. Okay, so likewise you can pump it up. So in other words, I can now have another R here. Okay, so that means then we get a copy of V squared, Y squared. So you can do this many times. So then you still have a string that's generated by T, but we want this to be S, right? So just in this diagram. So you remove them, you get to this diagram. You add one more copy, you get this diagram, right? So then what's left is to figure out a way to say this. Okay, the easiest way to say this is to look at context-free grammar in the Chomsky normal form, because that will be a binary tree. Actually, it's a it's a binary tree, and then the balance tree, a balanced tree, of course, we can figure out h in terms of the length of x, right? In terms of length of x, sorry, in terms of length of the length of the string it derives. So then from there on, we can find out what properties we must have. All right. So let's move back. Okay, now let's look at the pumping lemma for context-free languages. So let L be a context-free language. Then we know that there exists a positive integer p, and we call the pumping length such that for any string s in L, okay, which means s is either accepted by the PDA for L or generated by a CFG for L, such that when the length of x is greater than p, that can be converted to the height of the derivation tree is long enough, high enough, then s can be written as UVXYZ, satisfying the following condition. Number one, for any I greater than or equal to z, you can pump v and y, either pump it off, pump it up, or pump it down. So it's still in L. So this string is still in L. And the V and Y, at least one of them is not empty. So that means Vy, the length of Vy is greater than 0. And also Vxy, the length of Vxy is less than or equal to P. Okay, so that means that we find the two variables that appear more than one. We find one variable that appears more than once as close as possible to the root. Okay, so then we can get Vsy is less than or equal to P. So here's a proof. So since L is context-free, then we know that there is a context-free grammar in the Chomsky normal form that generates L. So now we look at a derivation tree T for any S in L, for any string S in L. And of course, we know it's a binary tree. And then a shortest binary tree, okay, is when it is well balanced and the height h is greater than or equal to log length of S. So when this h, so we want this h is greater than the size of v, okay? So that means that when the length of S is greater than 2 to the size of v, then h is greater than the size of v. That means then on a path, okay, on at least there is at least a path for, of this derivation tree with variables appear, with one variable appearing more than once. Okay, so there must be a variable r that appears more than once. Okay, so we simply select p, which is the pumping length, b to be to the length of v plus 1. Okay, so let's make sure that the derivation tree for any input s is tall enough. Okay, it's tall enough. So again, this is the things we saw. And so this is Vxy, as long as this part is long enough, as long as this part, we can, so we know that from R to R here, because it's a Chomsky normal form, it must generate something, right? So you must generate something. So remember, a Chomsky normal form is that S goes to AB, but then S does not appear in AB, and then it could be go in here. It could be empty, but after that, all the rules, you won't have S in it, and then you don't have the epsilon. You don't have epsilon. Oops. you don't have epsilon rule, right? So all the other rules will be something like this, or it goes to A. So this has to be a symbol, a alphabet symbol. So this means that from this R to this R, you got to generate something. Okay, you got to generate something. So that means this Vy, you got to generate something. It's not empty, so it's greater than 0. And then you push this R as high as possible, then you can make sure this part will not be too long. So in other words, you can make sure this part is less than or equal to P. So if it's longer than P, then you can just keep pushing it up, pushing it up, pushing it up until you find it. Okay. So that is the proof of this pumping lemma. All right, now let's see how we can use this pumping lemma to prove this language A to the n followed by B to the n followed by C to the n is not context free. Okay, so so when we use pumping lemma, we use it as a test, right? So the pumping lemma for regular language, for the regular languages is a test for regularity. And the pumping lemma for context-free languages is a test for context freeness, right? So then so when you are given a language at hand, you suspect that this language is not context-free, right? Because you can't come up with a PDA to accept it, or you cannot come up with a context-free grammar to accept it. But it is not approved because you cannot just say, I cannot come up with anything to do this, right? I cannot come up with a PDA. What happened if somebody else could come up with a PDA to accept it, right? So you got to show you cannot either. So that means that we want to prove if this language is context-free, then because we have this pumping lemma, we can apply the pumping lemma, and then we can derive a contradiction. And that contradiction indicates that your assumption that this language is context-free is wrong, right? So that is how we are going to construct this proof. So it's a proof by contradiction. So suppose that L were context-free. Then by the pumping lemma for context-free languages, there is a positive integer P. That's the, from the pumping lemma, P such that the conditions stated in the pumping lemma hold. Okay, so there are 3 conditions. Okay, hold. Now it's up to us to pick a particular string, okay, in L that is long enough. So obviously we can just pick A to the P followed by B to the P followed by C to the P. So it is in L, and also the length of it is 3 times P, of course, it's greater than P. It's greater than P. It's greater than, it's strictly greater than P. And so we can write S into the following 5 segments, U, V, X, Y, Z, with Vy not empty, the length of Vxy less than or equal to P, and you can pump V and Y down. Okay, so that means UXZ is also in L. So this is from the pumping lemma. So up to now, it's just from the pumping lemma. So up to this part is pumping lemma. Okay, so now next, we are going to demonstrate a contradiction. Okay, so however, these conditions imply that Vsy cannot now, because Vxy is less than or equal to P. So that means that it cannot span across 3 symbols, right? So you got A, so you got P many A's here. You got P many B's here. You got C many P's here. And then V X, Y is less than equal to P. So that means that you can either be in this segment or in the cross section of A, B, or in B, or in a cross section of BC, or in C. You cannot cross 3 segments. So when you remove Y, I'm sorry, when you remove V and you remove Y, then if this is in, it contains A or B, it doesn't contain C, that means that now you have more C's than A's and then B's. If VSY is in, if VSY does not contain A, does not contain the A, right, but it could contain B or C, then you remove them, then you will have more B's and C's than A's. So of course a contradiction. Okay, so this means that UXZ is a string where at least one letter has more occurrences than at least one other letter. Okay, depending on where this portion is, sometimes it may be more than the other 2 letters, but it cannot contain at the same time 3 letters, right? So VXY cannot contain 3 letters. So you pump it off, of course, that means that the other letters that's not contained in it will not be touched. Okay, so you have something that's not in L. So UXZ now is not in L, which is a contradiction. Hence, L cannot be context-free. Okay, so it's pretty straightforward. Next, we're going to see this example. So we have this language L, which is A to the I followed by B to the K, right? I copies of A followed by K copies of B followed by, okay, so followed by J copies of B. So this is J. And then followed by K copies of C, where I is greater than or equal to 0, less than or equal to J, and less than or equal to K, which is not context-free. So in this particular case, we have to look at where the VXY locates, right? So if VXY locates in the first half of it, we have to pump it up. In the second half, we can pump it down. So to break this condition, right? So the number of A's is less than or equal to the number of J's, and is less than or equal to the number of C's. So if we are, so you have, right? So you look at this. So this is A to the J, sorry, A to the I's. This is B to the J. Now it's going to be longer. This is C to the K. Okay, so if my VSY is in here, I gotta pump this I up. Okay, and otherwise, if my VXY is here, I can either pump it up or down, but if VXY is here, I still want to pump it down because that will, so I still want to pump it up so that it will have more A's or B's than K's. If my VXY is in here, then or here, I can pump it down so that I have more I's. Okay, so that's what we are going to do. So prove by contradiction again. So similar to previous example, we're going to select a particular string S, that's A to the P, followed by B to the P, followed by C to the P. It is in L because they all have the same number of copies, so A's and B's and C's, where P is the pumping length stated in the pumping lemma. So for this particular S we selected, it can be written in this form. So UVXYZ with Vy not empty. The length of Vxy is less than or equal to P. And then you can either pump it up or pump it down. This string is still in L. Okay. Again, depending on because Vxy, the length of Vxy is less than or equal to P, it cannot contain 3 symbols. 3 letters. It can only contain at most 2. So then we can make these things easier by looking at whether Vxy contains C or not. So if Vxy does not contain C, then we can pump it up. So because that means that your Vxy is either in A's, in B's, or in the cross sections of A's and B's, I can pump this Pn up. Okay, so I make it square. So that means we will have at least 1 more A's or B's than C's. Okay, so that violates this contradiction. So that pumping will generate, you said you generate a string in L, but in reality, it cannot be in L. Okay, so that's a contradiction. Otherwise, if Vxy contains C, that means that it cannot contain A. Okay, then we will pump it down. We'll pump it down so that you have more number of A's than B's or C's. We just pump it down. That's it. So that is a contradiction. You said by the pumping lemma, this string should be in L, but in reality, they cannot be because they violate the definition of your string. So, and hence your assumption that this language is context-free is wrong. And that is the pumping lemma proof for context-free languages. With that, we conclude this video. See you next time.